Hello, everybody. It's an exciting day here for Team Yugabyte. The 2.2 release with a significant amount of eagerly awaited features is now out there in the open for you to use, deploy, and give us feedback. So we are always there on our Slack and GitHub channels to help you out in case you face any issues. With that, let's dive right into today's topic, which is about Postgres compatibility. Before I get into Postgres compatibility itself, I wanted to make sure all of you who may be new to Yugabyte also understand what distributed SQL is and how Postgres compatibility is such a big step forward for the entire distributed SQL world. So first is, what is distributed SQL? The way we explain it is a revolutionary OLTP database architecture. And OLTP means for transaction processing, for serving real-time business critical data to your applications, which are mostly user-facing, and hence transactions, consistency, availability, scalability, all these are very foundational needs of those applications. Now, why is distributed SQL special? First and foremost, it is the SQL part, which is, it has support for relations and ACID transactions. So that's given. Second part is the distributed part. Now, the distributed part gives us three core benefits. First is the ultra resilience benefit, which is about natively healing the cluster of the database when there are failures happening at the disk level, at the node level, at zone, at region, at cloud, across the board. We live in cloud native era today where failures are essentially omnipresent. So ability to tolerate these failures automatically is a big plus for the distributed SQL. Second is the ability to scale horizontally, and that too for write requests. I would say traditional RDBMS has always scaled, has been able to scale read requests through read replicas, which are asynchronous copies, asynchronously replicated copies of the entire database. Where distributed SQL takes its step forward is, not only scales read, but it also allows you to scale writes by doing automatic sharding and automatic rebalancing of the data as the size of the cluster changes due to either addition of new nodes or removal of new nodes as a capacity planning exercise, or in the case of failures. Third aspect, which is a very significant and exciting aspect, and if 5 years ago somebody had told me that databases would reach this level of sophistication, I wouldn't have believed them, and that is about geo distribution. The ability to run a single database cluster, and that to a relational database cluster, stretched across 3 data centers with absolute consistency and transactional capabilities, with the ability to tolerate entire regions failure without without blinking an eye, essentially, and ability to reduce the latency of the requests that are happening for those local users in that particular regional data center. All these capabilities are now becoming core to distributed SQL databases. So now the sum total is what makes it more exciting. And as we'll see, PostgreSQL compatibility is sort of the icing on this exciting cake. Now, briefly as to why this is important, I touched on it, but summarizing it again, as we build more microservices applications, they need ability to do flexible data modeling, relational data modeling with SQL. You model your data one time, and then you can change your queries as your business requirement change is a very vital capability. And the ability to scale on demand without blinking an eye is essentially the need of those microservices application. Now, if we take an infrastructure first point of view, we live in the multi-cloud era. We have 3 large cloud providers building out data center capacity across the globe, and they are bringing to us lots of heterogeneous compute, storage, infrastructure, as well as this ability to run our app with the click of a button on any data center around the world. So which means that the ability to tolerate failures and the ability to geo-distribute data become super critical. The sum total is what distributed SQL gives us in the form of developer agility, build applications fast, operational efficiency, deploy applications easily, and last but not the least, ability for the business to roll out new applications faster. As a result, become essentially a critical player in the digital economy, especially in the COVID era. I would say, we have all become digital enterprises, more or less. It's the need of the hour. From an architecture standpoint, there is a minimum of 3 nodes in the database cluster, and those nodes each node stores part of the data that is present in the database through what is known as sharding or partitioning. Sometimes that's the word that is used, and these shards are also replicated in 2 more times into different fault domains. In this case, each node is a fault domain of its own. And this replication algorithm is usually Raft or Paxos because these are distributed consensus algorithms that help us build resilient systems easily. And as the size of the cluster changes, as you add more nodes or you remove nodes, the data continuously gets rebalanced and across the available capacity in the nodes. Now, this entire cluster of n number of nodes presents a single logical relational database using an SQL protocol or language to microservices. That's at the I would say, core of what distributed SQL architecture looks like. What is YugabyteDB? Now that I have introduced distributed SQL, YugabyteDB happens to be Postgres compatible, and that's why we are here. We'll dive a lot more into depth of that. Secondly, it's about serving applications with extremely low latency and high throughput, and as a result, high performance is a foundational design paradigm for YugabyteDB. It is cloud native. It is built in the Kubernetes era, and as a result, it understands the dynamic nature of spinning up pods, spinning down pods in a Kubernetes environment, and doing fast rebalancing across those fault domains inside Kubernetes becomes very important, especially for transactional applications, right? And last but not the least, it is fully open source, a 100% Apache 2.0 project that that developers can use without necessarily, getting sucked into any kind of fake open source marketing, which we are increasingly seeing these days from a bunch of other vendors, right? With that, I want to make a bold statement, and there are reasons why I'm making this bold statement, is that distributed SQL is the future of relational databases. We have learned to love, I would say, originally the likes of Oracle and SQL Server. They helped us take our, I would say, brick and mortar mainframe style applications and brought them to the internet world, right? And MySQL and Postgres did similar things on the open source side. But now we are no longer in the internet only era, right? We are in the digital era where, ability to build applications at the fastest rate possible is a competitive advantage. You cannot just have an internet app. It has to actually succeed in the modern cloud native infrastructure and microservices architecture era. So that's where YugabyteDB fits in. And we also have, we take inspiration from the proprietary architectures that came before us, like of Amazon Aurora and Google Spanner, okay? And that's what we're gonna talk about next. So Postgres compatibility in Yugabyte. So how does it actually work? I think it's, I will give you a little bit under the covers understanding of how this thing actually works. Now we all understand there is a single node Postgres architecture. It is a very popular, I would say, the most popular open source RDBMS on the planet today, clearly. And the way it is architected is there is a PostgreSQL query layer, which parses the client queries, analyzes, rewrites, comes up with a query plan, and then sends those execution primitives to the underlying storage layer, which stores data on a disk and gives and responds to the queries that are coming in from the query layer. Very simple, very easy to understand. This is how almost every traditional RDBMS looks like. So what the first thing we did at Yugabyte is to extend this concept into distributed SQL. So we took almost the same query layer native code as is, but brought it into a distributed form factor where that same query layer runs on every node of the distributed SQL cluster. But instead of interacting with this one node, storage layer, which essentially does not understand sharding, replication, geo-distribution, those three things that I talked about originally, we brought it on top of YugabyteDB's distributed store, which is known as DocDB. And DocDB is the Google Spanner-inspired document store that we built ground up using a custom version of RocksDB as the single node store, but then brought in the layer of notion of documents, advanced data types, as well as Raft-based replication and full distributed ACID two-phase commits style transactions. Is the job done? Wish life were that simple. The job is not done. We continue to push more of those queries down to the storage layer so that we can continue to increase the performance of the queries that are coming towards us. And this is a sort of an ongoing work where we have done tremendous progress since the project started, but we continue to push the envelope on this aspect so that we are pushing essentially the processing logic close to the data, as opposed to moving the data over network close to where the client is, right? And that will, if you push more data on the network, naturally your queries will slow down. The work essentially now is on the aspect of how do we continue to enhance the query optimizer? How do we give it more hints around where the tables are located, which shards are hot, and so on. And we are increasingly enhancing the PostgreSQL's native query optimizer to understand much of the distributed substrate. And this substrate becomes even more, I would say, exciting and challenging when you bring geographic distribution into picture, where location-based hints, how far a given node is from other nodes, becomes an important input into the query optimizer, because that's how we can reduce what is known as cross-region latencies even further, right? Cross-region latencies typically can become the dominant latency in a distributed database when you are deployed in a geo-distributed form factor. And overall, the idea is that as time progresses, our query optimizer will speak PostgreSQL obviously, but will become a sophisticated geo-distributed location-aware query optimizer that sort of again pushes the envelope of the distributed SQL architecture. So what have we achieved thus far? Thus far, we have achieved, I would say, a significant milestone of being able to support a wide variety of Postgres language features that cross the gamut of operators, expressions, expression-based indexes, partial indexes, table functions, row-level security, and so on. And like we are even able to run a bunch of Postgres extensions that do not necessarily interact with the storage layer and work only at the language layer. Because as time progresses, we'll continue to enhance the storage layer extensions as well to make it work on top of Yugabyte, but that's future work. Okay, the benefit of this depth that you see on day one by being so Postgres compatible is that we can widely integrate on day one with the rich Postgres ecosystem that we all have come to love over the years, right? Whether it be the language development frameworks with the likes of Hasura, Prisma, Spring Data, or the data visualization tools that are out there like dbeaver, Table Plus, pgadmin, they all essentially work out of the box. And we continue to improve I would say, the breadth of additional functionality that those frameworks may be needing, and also we improve the performance aspect by doing all the query push downs and query optimizer changes that I talked about. So, you know, it's an exciting start. A lot more work to be done. Coming to performance, now that the 2.2 release is out of the door, I'm excited to share our TPCC performance benchmark results, and we have so this release was a milestone release, because that's where we could get coverage on the language enough now that we can run the entire suite, TPCC as determined by the spec. And as you can see, for 10 warehouses, 100 warehouses, 1,000 warehouses, the efficiency, which is essentially the percentage of how much of the absolute efficiency can you achieve on those clients and data set sizes, we are right there with the top of the top, right? They are all close to 98, 99%. Now, is the work done? Again, work is not done. We continue to test against larger warehouse sizes with larger data sets. Work is ongoing for 10,000, 100,000 warehouses, and we'll be sharing those results over the course of the next few months. So summary is that distributed SQL is here. It is the future of the RDBMS. SQL, relational data modeling, and distributed asset transactions are very vital for modern app development. However hard the NoSQL world will tell us that they are no longer needed, we do not believe that to be the case, because developers still love the ability to model schema once and change queries later. Second is about ability to tolerate failures in the cloud era, ability to scale horizontally by just simply adding nodes, and not necessarily go through the pain of vertical scaling that we have all learned over the years in RDBMS. And giving this notion of a single logical database to the app, application and the application developer allows a sort of unprecedented, I would say, flexibility with respect to what you can build and how fast can you build. And all of us at Yugabyte are excited with the architecture, but we're also excited that we're bringing this entire form factor as a 100% open source distributed database to our community. Now, coming to Postgres compatibility itself, it is unique in the market with respect to its depth and breadth, because it starts out by reuse rather than a rebuild of the Postgres native query layer. And as a result, the team has put in, I would say, significant amount of work in ensuring that critical Postgres features that are important in the distributed form factor and app building vector are turned on day one. As a result, the depth of features supported is essentially unparalleled. Now, the depth also gives us an ability to spread our wings and integrate widely with the Postgres ecosystem. And if you have your favorite system that is not integrated yet, you haven't seen any documentation, you haven't seen any blog, then please reach out to us over Slack and GitHub. Let us know what are the additional areas that you think we should go towards. We will try to do it ourselves, or we'll also love to have you as a contributor to help us move the ball forward. That's it. That's what I had. Again, join us on our community, start us on our GitHub, use the software, give us feedback.